Hello AAF, aren't you glad to hear from me on the weekend? Given the snow and some of our other assemblies, field trips, blah blah blah, we are behind, so I'm going to have to teach you a lesson. Starting on Monday, I'm going to go on, and there is a book assignment with, a handout that goes with this lesson that's on math groups. Remember, on Monday I am also collecting the IB problem corrections, and you had remainder theorem problem handout, and you had long division problems to do from the book. So in today I'm going to do the lesson that I would have done on Friday, and also do a couple of long division problems at the end here just to go through, because you do have a quiz on Monday as well. Nothing from today's video will be on the quiz. Nothing from the lesson that I would have given you on Friday would have been on the quiz anyway. So it's all stuff that we covered before the break, and we went over on Thursday that big long warm-up that we did with long division and with higher order graphing of the polynomials and finding zeros and all that kind of stuff. So no surprises for the quiz and nothing from today's lesson. But I won't be teaching today's lesson in class. This is your only Friday's lesson. So this video lesson will be your only exposure to it. So, are you ready? Here we go. This was the warm-up that we were going to do together. And as you can see, I was planning on giving you back your tests as well so that you could look at that. Let me get this camera straightened out a little bit for you. So I was planning on giving your test back, so hopefully I will be able to get to that on Monday. Notice that this warm-up would be on, says no calculator. So if I were doing this on a quiz or a test, it would be on the non-calculator part. So without a calculator, find all the roots. And remember, synonyms for roots are zeros, solutions, x-intercepts if they are real. So as I'm thinking about root, zero, solutions, x-intercepts, I think to myself, what degree am I dealing with? So I know how many I'm looking for, because it just says all, it doesn't say how many. So I look at what I have here, and I have a second degree, an x squared, that will eventually have to get multiplied by this x squared. So that means I am actually degree what? Degree 4. Now, I said if I were to multiply this out. One of the biggest mistakes students make with conceptual errors, with problems like this, is they see these two things, and I'm going to just call them things right now, multiplied together, and they think, oh, I need to multiply that out. You are forgetting that to find the roots or the zeros, the solutions, the x-intercepts, you need to be set equal to 0. And to set equal to 0, I need to have not things multiplied together, but factors, factors multiplied together. And I've already got 2 factors set equal to 0. I know I'm a 4th degree, so that means by proof I have, and by theorem, excuse me, I have 4 roots. But since roots are zeros, solutions, or x-intercepts, I know that I'm looking for 4 of them, not necessarily all of them real. And how do I find the roots? The good F word, factor. And then students will go ahead and undo part of the factoring by multiplying this out back into terms. You already have 2 factors. You're equal to 0 because you're finding roots or x-intercepts. So you're equal to 0. So just take these 1, 2 things that are multiplied together and set them equal to what? Hello, 0. And then look, 2 very simple Algebra 1 problems. I don't need the quadratic formula. plus or minus 2. So I have a degree 4. I'm looking for 4 roots because it asked me to find all of them, and sure enough, here I have 1, 2, 3, and 4. So finding all the roots, answer the question. Roots, x-intercepts, solutions, 9, 1, 2, negative 2. If these directions had just said factor the following, I would have done the exact same thing, only I wouldn't have left my answer like this. I would have left my answer this way. If the directions had said to factor, instead of making a discrete list of 1, 2, 3, 4 roots or 4 x-intercepts, I would have used linear factor form, x minus the root, x minus 9, x minus 1, x minus 2, and x minus negative 2 or x plus 2. So that's an annoying -1 on a test because you've done the correct work. You would get all of the points for, showing that you understood that you were set equal to 0 and that you could individually factor each one of these quadratic pieces and that you would get all of the zeros. And then you just look back at the original directions. What was I asked to do? Find roots or find factors? And that would determine how you wrote your final answer. Don't forget, quiz on Monday, and there is a handout tonight that is on math groups called Write Your Own Equation. Okay? So let's go on with today's lesson, which is about writing your own equation. Oh, I forgot I had a mad face there for students that just messed this up, and it's really an easy problem, and I hate to see kids fumble on a problem like this by multiplying it out instead of just keep the separating going. All right, write your own equation. Write an example of a cubic my slides get messed up. Sorry, hold on 1 second for some editing. That one example that here was supposed to be last. I don't know how it got moved. All right, write your own equation. Write an example. And remember, we talked about this in class too, the vocabulary of the question. Write an example. That means that my example could very well be different from yours. It doesn't say write the particular equation. The particular equation means that I'm giving you points and we're all going to come up with the same answer. Notice that not only did they say to write an example, which means I have some flexibility in my answer, but they also told me the form they wanted in. So that again would be a read the directions and see what form they give. If they don't give you a form, then it is your choice. But I must put a cubic function, f of x, in this general form where it's not factored. So this problem is testing your knowledge of a theorem without ever asking you to write the theorem out. If I give you roots or zeros or x-intercepts, I give you 3, which is good because I told you I have a cubic function. And by theorem, cubic functions have exactly 3 roots. Some of them may be real, some of them may not be real, but they are 3 solutions. Now they gave me 3 of them, and all 3 of them are real, 5, 1, and negative 3. Also, you are writing an equation, so write f of x is equal to x minus, and x minus, and fill in the roots, 5, 1, and negative 3. Clean up the double negatives. That's the equation, and I would stop there if they hadn't told me that that form was not acceptable. So they're telling me that I must put it in to general form, which means I have to expand this out. My answer again is correct. It is an example of a cubic function with those roots, and I have written an equation, but I haven't matched their form. To match their form, I'm simply going to practice Algebra 1. A long time ago in elementary school, I learned that multiplication is commutative, so it matters not which one of these factors I choose to multiply. For instance, if you had to multiply 5 times 1 times negative 3, you could multiply the 5 times the 1, get an answer, and multiply times negative 3. Or you can multiply negative 3 times 1, get an answer, and multiply times 5. Or you can multiply the 5 times the negative 3, get an answer, and multiply times the 1. Things are no different here. You have 1, 2, 3 things to multiply together. Pick 2 of them, multiply and get an answer, and then multiply the third. Students who have a very clear understanding of what to do in this scenario, nobody would take the 5, multiply it times the 1, and the 5 and multiply it times the negative 3, will ask me about whether they should multiply the x minus 5 times both of these other factors. What works for numbers has to work for things that hold the place for numbers. So I'm just going to go left to right, and I'm going to pick these two and multiply them together. I've practiced my Algebra 1 enough that I don't have to laboriously write everything out here. There's my first two factors times my third. Now I'm going to distribute, just like I did before. I just have a couple more, instead of multiplying a binomial times a binomial to trinomial times a trinomial. No big deal. I'm just distributing here and getting x cubed plus 3x squared. Now multiply here and here, and I get negative 6x squared minus 18x. The plus 5 gets a turn here and here. And I get, combining like terms, my cubic function in general form, x cubed minus 3x squared minus 13x plus 15. That is an example. Here's another example. If I had put a 2 in front of there, or a negative 2, or just a negative 1, I would end up multiplying just like I had before, but then when I was done, I would distribute my dilation factor. And I would have another example of a cubic function, but guess what? They would still have the zeros of 5, 1, and negative 3. Let's look at this for a second. Get out your calculator. And put this function into y1. X cubed minus 3x squared minus 13x plus 15. With a y-intercept of 15 that I can see from right here, right, and a cubic function, so I know what the ends look like, I made my window, my y-min and my y-max, go to 30 and negative 30, because I knew I had to go to at least 15 in the y-min. I'm sorry, y-max with a positive. So I knew my zeros were 5, 1, and negative 3, so my x-min and max of negative 10 was just fine. But I made my y-min and y-max go to 30. And when I graph this, I am not shocked to see the end behavior here and here. Okay, behaves like a linear function. And if you hit trace, trace, and you hit -3, shockingly, the y value is 0. 1, the y value is 0. And 5, the y value is 0. Supposing that I had made the leading coefficient -1 instead of 1, this equation would have looked like -x cubed, just distributing my -1 through, plus 3x squared, plus 13x, and minus 15. So with a negative leading coefficient, I'm going to expect my end behavior to switch, which it does. So I have a different cubic function, but guess what? If you hit trace, and you hit -3, oh my gosh, whoops. If you hit -3, you get 0. If you hit 1, you still get 0. And if you hit 5, you still get 0. Guess how many cubic functions there are that have zeros of 5, 1, and -3. An infinite amount, but they all have the same linear factors, x minus 5, x minus 1, and x plus 3, differ simply by a dilation factor. Crazy, eh? All right. Next, that was a cubic function that had 3 real zeros. This is what I did. I turned my roots into linear factors and I expanded them. So that process can't change when I have, shockingly, non-real zeros. Okay? If I'm asked for a cubic function, if I'm asked for a quartic function, I don't care what the degree of the function is, as long as I have the zeros, the x-intercepts, the roots, the solutions, be they real or not real, I can write an equation that represents that function with those zeros. All I do is turn the roots into linear factors, and remember, I don't expand unless they make me, right? If somebody just asks me to write an equation given some roots or some zeros, I will just write the linear factors. I will not expand unless they tell me to, and they might tell me to by saying expand, or they might give me the form that I'm supposed to give it to them, that they want to see the answer in. So look at this one. Write an example of a cubic function in general form. Notice this time they didn't tell me what general form was. Back here they were nice and they actually wrote out general form. They don't have to. They're expecting you to know what the general form of a polynomial is. If they're nice and give it to you, good, but they might not. Again, this is why it's important to write down directions. For this one, write an example of a cubic function in general form. That means expand the linear factors. So a cubic means I'm expecting 3 zeros. 2 and plus and minus I, that's 3. So first, write the linear factors. I just used f of x in the last example, so I'll use g of x this time. It's cubic, so it's x minus, and x minus. Fill in the 2, fill in the I, and fill in the negative I. So, just like before, you have 3 factors now to multiply together. When I see cubic functions in general form, I don't see any i's in it. So I'm expecting that expanding is going to make these i's disappear. Right now I've got i's. You can pick any 2 factors, multiply them together. I suggest that you choose the non-real ones first. Just a suggestion, not a mandate. I'm going to multiply those together. Now I recognize that because I've done so many of these problems. In Algebra 1, by the way, doesn't matter that I didn't do them with I and negative I, but I recognize this pattern. X minus I, x plus I. Those are conjugates. Okay, so they have i's in them, so they're complex conjugates. Nevertheless, I know what I'm going to get. I'm going to get x squared. The middle terms, negative ix and positive ix, are going to drop out, and I'm going to get negative I squared. But by definition from Algebra 2, what is I squared? Negative 1, so x minus negative 1 is x plus 1. Lo and behold, my i's are gone. Bye. There's my quadratic factor, but I still have a linear factor left. Multiply. The x times the x, and times the positive 1. The negative 2 times the x squared, and times the positive 1. In general form, the powers decrease in order, so this would be x cubed minus 2x squared plus x minus 2. Cubic, check. General form, check. Did I use 2 and plus and minus I? Check. I's all gone? Check. I have a cubic function, starts increasing, ends increasing, because I know what the end behavior of a cubic function with a leading coefficient that is positive does, has a y-intercept of negative 2. Just because I feel like it, I wonder if this cubic function has extrema or not. Remember, we have a formula to tell if a cubic function has extrema. A, B, C, and D. B squared minus 3AC then is negative 2 squared minus 3 times 1 times 1 which would be 4 minus 3, which is 1. Since b squared minus 3 is positive, this cubic function has 2 extrema versus the kind of plateau looking thing or the almost no, almost looks straight but not. 2 extrema. Alright. Here's another one, and I've thrown 2 things at you. Number 1 the complex 0 that I gave you is a little nastier than just the plus or minus I gave you before, so that's going to be a little bit of a curveball. Also, notice what they are testing here. They've given you a cubic function. By theorem, you know the cubic function has 3 zeros, and yet look how many they gave you. They only gave you -3 and 2 plus I. What are they testing? They're not expecting you to find the 0 out of the air. That's right. They are testing to see if you understand that complex zeros always come in pairs. So if they gave you 2 plus I, by default, they are also giving you 2 minus I. And there's my third, which matches up with the cubic. Okay, so watch out for that. Clever test writers. All right, I'm going to use H this time, right? I don't have to, of course. Cubic means I have 3. I could call them all F because they're different problems. So, I'm going to start this just like I do before. Take my roots, my zeros, turn them into linear factors. X minus, X minus, X minus. Put the -3 here. Clean up your double negative. Now, I am going to show you how this is not a mandate, this is how I deal with 2 plus I and 2 minus I. I don't distribute. I don't distribute yet. I kind of treat the 2 minus I and the 2 plus I look at that in my head and I just see one thing. I see I and -I. I even see 5 and 3. You know, I'm just going to treat those blue groups as its own entity for now. And just like I suggested before, I am going to multiply the 2 complex factors and leave the x plus 3 till the end. What happens when you multiply x times x? Shockingly, x squared. What happens when you multiply x times negative crap? You get -x crap. What happens when you multiply negative crap times x? You get -x that crap. What happens when you multiply negative crap times negative other crap? You get positive that product. Crap times other crap. Now, step back and look at that for a second. And look at this piece. I recognize that piece. That is complex conjugates. And I don't have to distribute this out because I've done this enough. I know that complex conjugates is always the real number squared and then the real coefficient squared and added. If that pattern doesn't make sense to you, make up 10,000 complex conjugate problems and multiply them out. That's how you get to recognition quickly. Now I'm going to deal with this. Now I'm going to distribute and say that's -2x plus xi and -2x minus xi. And then of course I still have this x squared. Look what happens. Bye. The eyes. Ooh, those kind of look like angry eyes, don't they? The eyes that existed here and still existed down here, all of a sudden went bye. As they should. You don't see, in our world, cubic functions with eyes in them. So this quadratic factor is x squared minus 2x, and minus 2x is usually minus 4x, and plus 4 and plus 1 is usually 5. There's the quadratic factor. Don't forget that we had the linear factor here. And now I am just going to distribute. And I get x cubed minus 4x squared plus 5x and plus 3x squared minus 12x and plus 15, my y-intercept. Clean this up. Right? X cubed minus x squared minus 7x plus 15. Cubic function. An example. This again is just an example. If you wanted a different one, well, throw a 4 in front of here. Okay? Throw a 41 in front of there. Throw a negative 2 in front of there. That would change the signs and the coefficients. Right? But you would still have 1 0 at negative 3, and you wouldn't see any other zeros. Let's put this one into our calculator. X cubed minus x squared minus 7x and plus 15. Sure enough, a cubic function starts increasing, ends increasing, has two extrema, which means had I calculated b squared minus 3ac, it would be what? Not negative, not 0, would be positive, telling me I have two extrema. Not all cubic functions have extrema, remember. But notice how many real zeros. Only one, and it's at negative 3. Why, that's crazy. Notice back here, after I was done getting rid of the i's, that I ended up with a quadratic factor times this linear. And I want you to reflect back on when we were doing this backwards. In other words, when I gave you the cubic function, like this, I could have given you h of x, given your calculator, and said, find all the zeros. This could be on your quiz, right? Where I would give you your calculator, so you would put this into your calculator, and I promised you that every time you do this for me, you would have nice zeros, and you would have as many as you need to complete long division. So if this problem was on a quiz, here it go, you put it into your calculator, you found the one real zero at -3. Then you would have taken you would take that real zero of -3, turn it into a linear factor, whoops, you would have turned it into a linear factor, so x minus -3 would be x plus 3, and then you would have divided into what I gave you, x cubed minus x squared minus 7x plus 15, right? So this is good practice for your quiz. What do you multiply x by to get x cubed? And you say to yourself x squared. X squared times x is x cubed. X squared times 3 is positive 3x squared. Draw your line, add the opposite, bring down. What do I multiply x by to get -4x squared? Self, that's -4x. -4x squared minus 12x. Draw your line, add the opposite, bring down the 15. Self, what do I multiply x by to get 5x? Why, that's a plus 5. And I get 5x plus 15. And when I add the opposite, I get a remainder of 0, which, because I started with a factor, LF for linear factor, I knew my remainder should be 0. And look what you have here. Look what your answer on top was. X squared minus 4x plus 5. Where have you seen that before? There. X squared minus 4x plus 5. OMG. Guess what would happen if you took x squared minus 4x plus 5 right? That was on top of the division. What did I teach you to do? Find all the zeros now. Once you depress to a quadratic, you take this quadratic over and you use the quadratic formula to look for the other zeros, and you get -b plus or minus, whoops, I'm sorry. Yes, -b plus or minus the square root of b squared minus 4 times a times c, all on top of 2a, which is 4 plus or minus the square root of 16 minus 20 over 2, which is 4 plus or minus the square root of -4 over 2, which is 4 plus or minus 2i over 2, which is 4 over 2 plus or minus 2i over 2, which is 2 plus or minus I, along with -3 drum roll, right? I told you to write an equation with the zeros of -3, 2 plus I, 2 minus I. You got it down here. And then shockingly, when I divided to undo all that multiplication, I got right back to negative 3, 2 plus I, and 2 minus I. Math is beautiful. Oh, crap. I was trying to write math is cool. You get it. All right. So that was, that's what your handout is tonight. Tonight, the handout on math groups gives you 3 problems to write out the equation, 2 cubics and a quartic, I believe. And you take the linear factors that I give you, even if I don't seem to give you enough, right? Like this one. It didn't look originally like I had given you enough zeros. I said a cubic trying to erase all the, right? I said a cubic. And it looked, you know, when I gave you just 2 plus I, looked like I only gave you 2 zeros, so watch out for that. Then on the handout, it also says to take the equations you got from number 1 and 2 and graph and label them completely. So that's good practice for your quiz. And I'll put up on math groups, not only will the worksheet be there, but so will the solutions, so that you can use those to check writing your equation, which won't be on the quiz tomorrow, but the graphing could be on the quiz, because that's old news. Before I let you go, I did want to do, I just did a long division problem with you, but I want to do a couple more, and I just pulled some more from the book to go over and do with you. So I'm just going to get up a clean slide, and I'm just going to do some random division problems. Again, this is old. So these were from page 346 in your book. I know I gave you some of these problems for homework on Thursday. I don't remember which ones I gave you, but I'm just going to do a couple with you. The first one was x cubed was a cubic. So remember back in unit 1 where it was like, well, we're not actually dividing functions, we're just going to write one on top of the other and talk about if this was a function, you know, what the domain restriction of -2 could not be put in for x, obviously. But now you are older and wiser, and we can actually divide this. Since I don't know, no one said put this numerator, this cubic, into the calculator and see if -2 was indeed a 0. I don't know whether my remainder is going to be 0 or not. I do know that whatever remainder I get is the y value that goes with not 2, but -2, if you were to plug in -2. That's part of the remainder theorem, right? So by doing this division, whatever the remainder is the same thing as if I had taken the numerator and plugged in -2. Because remember, a linear factor is x minus, right? If it is a factor. I don't know whether it's x minus the factor, or the 0, I should say. All right, so I'm going to divide. Since this is a cubic and I'm dividing by a linear factor, I should get a quadratic on the top. So, self, what do I multiply x by to get x cubed? Add the opposite. Can't tell you how many times people think that's 0. What do I multiply x by to get -4x squared? opposite. What do I multiply x by to get 5x? Add the opposite, and I get a remainder of 2. Since I have a remainder of 2, I know that x plus 2 is not a factor of the cubic, but I do know that if I were to plug negative 2 into the numerator, I would get 2. This was not what they asked me, however. This was just in my head. They asked me for the answer to this division problem. The answer to this division problem is the cubic that I got, the quadratic that I got by dividing, and my remainder when I was dividing by x plus 2. This is the answer. I can always check my answer to division by doing what? Multiplying. If I multiply my answer times what I divided by, I should get what I was dividing into, right? I mean, that goes back to, right, 2 into 25. How many times does that go? Right? With a remainder of what happens when you multiply 2 times 12 and a half? You get 25. So, let me check this out. What is x plus 2 times x squared minus 4x plus 5 plus 2 over x plus 2? I'm going to distribute. And I'm going to get x squared times x plus 2 minus 4x times x plus 2, 5 times x plus 2, and 2 over x plus 2 times x minus x plus 2. Just made it a different color to make it clear what I was doing. Multiply x plus 2 times everybody. What happens? X cubed plus 2x minus 4x squared minus 8x plus 5x plus 10 and bam, bam, plus 2. Putting everybody that matches together, negative 4x squared and negative 2x squared, gives me negative 2x squared. Negative 8x and positive 5x is negative 3x, and 10 and 2 is usually 12. Gasp! Math is cool. Okay. Next one. That was number 1 on that page 346. I wanted to do number 3 with you because number 3 is technically not in what we call in pure linear factor form. 2x plus 3 was in the denominator. And 8x cubed plus 10x squared minus 13x minus 20 was in the numerator. Now this still is a cubic divided by a linear factor. I'm going to get a quadratic when I'm done. But you can't make the same generalizations about this is not in linear factor form. Remember, linear factor form, to be in linear factor form, you have to be in x minus c, where c is a 0. Or remember to use the remainder theorem where I don't necessarily know if c is a 0 or not. They called that b. Notice the coefficient, though, both times of x is 1. So in reality here, this is not a linear factor. Now I can write it as a linear factor. That way. So I'm really talking about, is negative 3/2 a 0 or not? But none of this is really necessary, right? Because they just are asking me to divide. That's all. They're saying, take this cubic, divide it by this first degree, and tell me the result. So fine. Self, what do I multiply? 2x to get 8x cubed. Add the opposite. What do I multiply 2x by to get negative 2x squared? Whoops. Add the opposite. What do I multiply 2x by to get negative 10x? I get a remainder that is not 0, so I have to say my answer is the quadratic that I got, and the remainder over what I was dividing by. Of course, a plus minus could be written that way. Either way is fine. Alright, so I did a typical division problem with a remainder, showed you how to write it, and that was when we had a leading coefficient of 1. This time I did a division problem, still a linear factor, or I keep saying factor, a linear term, dividing a third degree by a first degree, getting shockingly a quadratic. But the leading coefficient of what I was dividing by wasn't 1. Now I'm going to do another problem where I'm dealing just with a cubic again, and I'm going to divide by a very simple x plus 5. But there's a trap. It's a trap. So I have a third degree. I'm dividing by an x to the first, so I expect a quadratic when I'm done. I start off just like I always do. Self, what do you multiply x by to get x squared? I'm sorry, x cubed, and it's x squared. And I add the opposite, and I get 2x squared. And there's two ways I can think about this next. I'm missing, this goes, every polynomial is ax cubed plus bx squared, or cubic I should say, plus cx to the first plus d. The c, just in this case, is 0. There is an x to the first, so I can kind of sort of think about it. I have 0x to the first here, and I bring that down. And I continue on my way. What do I multiply x by to get 2x squared? Add the opposite. That's a minus, right? Minus 49. What do I multiply x by to get negative 10x? So my answer is my quadratic. And my remainder over what I was dividing by. You could, again, you don't have to think of it that way. You could just have as long as you realize that when you were at this point and you got 2x squared and brought down the negative 49, that you would say, what do I multiply x by to get 2x squared? You would still have multiplied by 2x, and you would get 2x squared plus 10x. Add the opposite, and these of course go away, and then when you're adding things that aren't alike, you just say you're adding them. I'm going to add negative 10x, and I just put the linear thing first. I'm going to add the negative 10x and the negative 49. And then I go on my merry way. What do I multiply x by to get negative 10x? I would get negative 10. And I would have gotten my 1 and get to the same answer. But sometimes having this missing term here causes kids either to stop working, they're not sure what to do, or they think this is a linear term and they combine the 49 and the 10, and just sad things happen. So watch out. I mean, it's the same thing you did in elementary school when you basically had to worry about placeholders. You know, when you were dividing 3 into 1001, you had to worry about these, you know, making sure you maintained the placeholders. It's exactly what you're doing here. All right. I wanted to do, you know, you can stop watching at any time now. I'm just doing some practice division problems. I picked a couple more. I picked this one. Because I was dividing a 4th degree by a 2nd degree, and I had 3 terms. what I was dividing by, right? Students in Algebra 1 get all crazy sometimes, and they start canceling out terms here. Ah! Please tell me you would not be tempted to do any such thing. Now I'm dividing a fourth degree by a second degree, so I expect a quadratic out of this, right? X to the fourth over x squared. I am not frightened by the fact that this doesn't look exactly like everything I've been doing before. I have an algorithm, a recipe for dividing, and I'm going to follow it. What do I multiply x squared by to get x to the fourth? X squared. X squared times x squared is x to the fourth. X squared times x is x cubed. X squared times 1 is x squared. Now this kind of goes to what I was talking about before, right? Be careful about what matches and what doesn't. I'm going to add the opposite, but you can only add like terms. Hello, Algebra 1. These go away. I have a negative x cubed and how many x squareds? Right? I got no x squareds left. So I will bring down the plus 1. Then I will say to myself, self, what do you multiply x squared by to get negative x cubed? And I get negative x. Negative x times x squared. Negative x times x. Negative x times 1. Add the opposite. Matching terms, different signs go away. X squared had nothing to match with, and it's positive. X had nothing to match with, and it's positive. 1 had nothing to match with, and it's positive. What do I multiply? Hey, those look the same. X squared plus x plus 1. I bet if I write plus 1 up here, I get a remainder of 0, which tells me something. That tells me that x squared plus x plus 1 is a factor of this fourth degree. So if somebody, nobody asked me, but if somebody asked me to factor this, I know that 2 of the factors look like that. Hey, I messed that up. X squared plus x plus 1 times x squared minus x plus 1, because I have this remainder of 0, must mean that those two are factors of x to the fourth plus x squared plus 1. Nobody asked me to break it down further, and I could try, you know, and so I could factor these by inspection because they're quadratics. If they didn't factor, I would use the quadratic formula and I could get all the linear factors. No one asked me to do that. This was just something I couldn't help noticing when I get a remainder of 0. Notice the answer to that problem, though. The answer, when they just said divide, this is my answer. I mean, if you really, really want, if it makes you happy, you can say plus the remainder. But why would you?